Now we want to actually come up with some electron configurations, and we're going to start with standard notation. The idea behind standard notation is for an atom, you give every single subshell where there are electrons and how many electrons are in there. So standard notation is standard, kind of one of the basic representation of just where are the electrons and importantly, how many do you have? So if we look at, for example, nitrogen, we can see there's this writing out, and how we would say this is 1s2, 2s2, 2p3. So that's an overall description of all of the electrons. It's all about taking these ideas, how many subshells, how many countings, electrons, putting it all together, accounting where the electrons are. We can see that the subshells are written in order of increasing energy, and then those exponents, the numbers that are raised as subscripts, are the numbers of electrons in that subshell. So if we parse this out, nitrogen 1s is the lowest energy subshell, so it's first. And for nitrogen, there are 2 electrons in that subshell. That corresponds to being a full subshell. We then move up. There's more than 2 total electrons in nitrogen, so we go to 2s. And we can see that there's, again, 2 electrons in that subshell, right? These exponents, 2 and 2, indicate how many electrons are in those subshells for this atom. We keep going up. 2p has then 3 electrons in the subshell. So we can see that this is a complete count of all of the electrons in there. Nitrogen is atomic number 7, so a neutral atom has 7 electrons. If we add up those subscripts, 2 plus 2 gives you 4. You add 3, you hit 7. So that's all of the electrons. You will note then we don't have any other subshells written. It is possible, we know that past 2p, next highest energy would be 3s, but we don't need to put anything in there. So we don't say it's 3s0 or something like that. We just don't write it. We don't write higher energy subshells that don't contain electrons. Let's come up with some electron configurations then. So we'll start with hydrogen. This is the smallest atom. It only has 1 electron. And so we start by asking the question, what is the lowest energy subshell? We know based on the Aufbau principle, that's the first thing we're going to fill. So on the bottom, I have a listing of all the subshells. We can see the lowest energy is 1s. Hydrogen, so 1s is where we're going to start. How many electrons can we put into a 1s subshell? Well, it's based around being an s-type subshell, so it can hold a total of 2. So that means the hydrogen has a single electron to put into a 1s. The max capacity is 2. We only need 1 in there. So the electron configuration for hydrogen is going to be 1s1. If we bump up to helium, we now have 2 total electrons because helium is atomic number 2. So a neutral helium atom has 2 electrons. We start by asking the same question. What's the lowest energy subshell? And we get the same answer of 1s. Right? That answer is always going to be 1s. And then, so what's the max capacity for 1s? That's always going to be the same answer of 2 electrons because it's an s-type subshell. Helium has 2 total electrons. The 1s can hold 2, so they both go in there. So we get a 1s2 configuration for a helium atom. Lithium, atomic number 3, now has 3 electrons. When we go to ask the question, what's the lowest energy subshell? Again, we get 1s. The 1s subshell can hold 2 electrons. Well, lithium has 3, so it's going to go ahead and fill up that 2. But now we need another subshell. The next lowest energy is going to be 2s. So we can see 1s2, 2s1. So one of the things we can start to see, this idea of the Aufbau principle means building up. And what that building up, how that is reflected in forming these electron configurations, is that we started with helium has 1s2. Lithium having 3 electrons, the first 2 are going to go into the same 1s subshell because it's still the lowest energy. So when you're forming the electron configuration of lithium, it builds upon the electron configuration of helium. It starts in the same way, and then you just keep building up upon it. Those first 2 electrons are always going to go into 1s2. Doesn't matter what the atom is. As long as once you hit 2 electrons, the first 2 always go into that 1s2 subshell. If we go to boron, this is atomic number 5. we know it's going to start in that same way. 1s2 because the first 2 electrons go into there. The next lowest energy subshell is still the 2s. So boron has 5 total electrons. So the next 2 go into 2s. Then we finally click to what's the next highest energy, 2p. So then that 2p does go, the single electron does go into that 2p state. So boron is 1s2, 2s2, 2p1. We can see with neon, this is atomic number 10. We can see that we would expect that the first couple will be 1s2, 2s2. If those are full subshells for boron, when it is at 5 electrons, since neon has 10 electrons, it's more than 5, those full shells are still going to be full, right? Once you're past 4 total electrons, everything is going to, that initial part is always going to look like that. And then the next highest energy subshell is still 2p. Because it's a p-type subshell, it's changed, it's no longer s-type, it's p-type, your max capacity is now 6. So the max capacity is now 6, neon with 10 total electrons, 2 plus 2 plus 6 is 10. So we have fully accommodated all 10 electrons. Silicon, if we want to keep going up, is atomic number 14. So the first 10 electrons we can see match what we had with neon because those were all full. So these are all full as well. When it's all full for neon, those first 10 are going to go to the exact same place. So you're building up. Silicon has 14 electrons. The first 10 go to the exact same full subshells because the Aufbau principle that's listed on the bottom here, those orders never change. The ordering of orbitals never changes, and so then it's just a matter of filling it up. 3s is next, then 3p. We've accommodated all of our 14, so we're done. We're going to look at some more examples of writing standard notation electron configuration. I have beryllium, oxygen, sulfur, and chromium. And so these are 4 that I want to be able to write electron configurations for. And so if I take a look at those, I know the first question I always want to ask is how many total electrons do I have? How many electrons am I trying to assign? Because I need to know how many I'm putting if I want to figure out where they're going to go or how many go in. And then I just fill up the orbitals starting from the lowest energy. And I determine what that energy ordering is based off that Aufbau ordering. We don't need to memorize those subshells. We just fill up those subshells starting from the lowest energy. And each orbital is capped at 2 electrons. So we know then in an s subshell, because there's 1 orbital, 1 times 2, 2 total electrons. In a p-type subshell, 3 orbitals, 2 electrons per, gets me 6. In a d-type subshell, 2 electrons per orbital, 5 orbitals, gets me 10. So if I want to take a look, then beryllium has 4 total electrons. And if I look at my Aufbau ordering, so I always want to get that Aufbau ordering and figure it out. You can see that the lowest is the 1s. Okay, I have 4 total electrons to put in beryllium. 1s can only hold 2, so 2 electrons go in there. And so then I have 4 minus 2, right? There was 4 electrons that I started with. 2 have been assigned into the 1s2. So I have 2 more electrons. So I go to that next highest energy, and that's going to be the 2s. So I'm going to put my next 2 electrons into that 2s orbital, 2s subshell. And that 2s subshell can hold 2 total electrons. So now I can see I have the 2 and the 2. Those add together to give me 4. So my 4 electrons of beryllium give me a 1s2, 2s2 configuration. Oxygen is 8 total electrons. I know I want to ask these questions of, what's the lowest energy? And I know for beryllium, I already answered for the first 4. It was 1s2, 2s2. So I'm going to go through the same process. I'm going to get 1s2 for the lowest energy, and then it's going to be 2s2. We can see that in beryllium, those first 4 electrons filled the subshells. And so the first 4 electrons of oxygen go into the exact same subshells because we're asking the exact same questions. We get the same answers. But now my 2 and 2 does not equal 8. So I have some more electrons that I need to assign
and that's where I go to the next highest energy, which is going to be 2p. So I have 8 total electrons for oxygen. 4 have already been assigned. That means I need to do 4 more. 2p, because it is a p-type, can hold 6 total. 4 is less than 6, so 2p4. Again, I can see that I have 2, 2, 4. If I add all those up, 2 plus 2 plus 4, that is 8 total electrons for the entire oxygen atom. If we take a look at sulfur, that is 16 electrons. We can follow the same, ask, what's the lowest energy? We know where does that go? We're going to get 1s2. Then we know we're going to fill 2s2, because if 8 electrons filled up all those orbitals, 16 electrons is definitely going to fill those subshells. And now we get to a slightly different point than where the O was, right? O couldn't fill 2p. That still is going to be the next lowest energy for the sulfur atom. But now, if I have 2 assigned out of 16, I have 12 electrons left to assign. 2p can only hold 6, so it'll take all of those. We're going to fill up the 2p at a full 6 electrons. So that's going to get filled up. We want to ask, we still have more electrons. The next lowest energy is going to be 3s. 2, 2, 6, that's 10 total electrons. So 16 minus 10 is 6. We got 6 more electrons. This 3s can only hold 2, so we'll go ahead and put all of them in there. And again, that comes from the fact that it's s-type. So 3s2, we still have 4 more electrons to assign. The next highest energy is 3p. 3p, because it is a p-type, can hold 6. 4 is less than 6, so we'll go ahead and put all 4 inside that 3p. So we can see with sulfur, there's more electrons in there, so it gets to be a bit longer. Chromium, our final example here, is 24 total electrons. And we're going to start, 1s is going to be 2, 2s, 2. We can see anything that was full in sulfur is still full here in chromium, 2p6 and 3s2. These subshells were completely full, and as a result, they show up in chromium. Chromium has more electrons, so the same subshells that were filled in the S or sulfur have to be full in chromium, in this Cr atom. But we need more, right? That gets you to a total of 12. Chromium has 24 electrons, so we need 12 more. So we ask that question. The next highest is 3p. The next highest is 3p. That can hold 6. We need more than that, so we're going to fill up that 3p6. So then we're now sitting at 18 total. We need to do 6 more. Next highest energy is 4s. Because that is s-type, it can only hold 2. Okay, so we know that can hold 2 more. We'll fill that up. So now we have 4 left to go. And the next highest energy is 3d. Because it is a d-type orbital, that can only hold 10 total electrons. And so 4 is less than 10, so we just put all 4 into that 3d subshell. And so we can see then that this chromium, all 24 electrons have been assigned. Importantly, everything that was full here matches up. We can also see that, everything like back here, the 1s, 2s, we can see that is maintained through everything. Anything with more electrons than beryllium, anything with more than 4 electrons, the first 4 electrons all fall into that exact same pattern as we just keep building up. Because the subshells follow the same energy ordering, as a result, we get the same patterns of just kind of an expansion on that kind of similar pattern of going on. Anything more than chromium, right? If we think there's kind of this pattern of filled shells in chromium, anything with more electrons than chromium, all those subshells are still full, and the 3Ds just get more and more electrons in them until eventually that gets full, and you move into 4p, then 5s, and so on and so on. It just keeps going up. So this Aufbau principle, this idea of building up, that ordering is always the same. So the bottom of the periodic table and the bottom right is oganesson. That's number 118, 118 electrons. If you put all of those electrons into the orbitals, you would get the following electron configuration. Now, this is really long. You can see this is starting to become a bit of a pain. But importantly, this 118 contains, it's built up on all the electron configurations of all the smaller atoms on the periodic table, right? We can see the same patterns we saw previously, right? 1s2, 2s2 of beryllium. We can get the 1s2 all the way up to the 3s2 that we saw, or it was 3p6, sorry, for silicon. Following through there, you know, we can get then the pattern we had up to chromium, right? We can build upon those, just keep growing and growing. There's just all the higher energy orbitals were empty for those smaller atoms, but not for something big like oganesson.
Participation 622, question 2. Write the electron configuration of the following atoms: carbon, aluminum, titanium. This is the second question on participation 622, due Monday, June 22nd at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, write the electron configuration of the following atoms: carbon, aluminum, and titanium. Okay, how did participation question? Participation 622, due Monday the 22nd. Looking for any more questions. Got a couple more videos left. See you there.